Antihydrogen is real. It is the perfect mirror image of the hydrogen we find all around us. For every particle in a regular hydrogen atom, antihydrogen has an antiparticle. Where hydrogen has a proton and an electron, antihydrogen has an antiproton and a positron. It is a tiny, fleeting piece of a universe made of antimatter. Here at CERN, one of our great scientific quests is to create these anti-atoms, hold them still, and ask them some of the biggest questions we have about the nature of reality itself. The work is difficult and precise, but it is a journey we must take. The most important fact to begin with is this: we can do it. Scientists at CERN have successfully created and trapped antihydrogen atoms. This isn't just a theoretical idea or a fleeting blip on a screen. We have held on to these anti-atoms not just for a fraction of a second, but for over 1,000 seconds at a time. This achievement is monumental. It proves that antimatter isn't just a concept from science fiction. It is a tangible substance that we can produce and study in a laboratory. This ability to hold on to antihydrogen is the key that unlocks a whole new realm of experimental physics, allowing us to probe its properties with incredible precision. The reason we go to such extraordinary lengths to make antihydrogen is to search for an answer to a profound puzzle. Our best theories of physics, particularly the Standard Model, suggest that the Big Bang should have created equal amounts of matter and antimatter. Yet, when we look out at the universe, we see stars, galaxies, and planets all made of matter. The journey to making a single anti-atom begins with an act of incredible power. We need antiprotons, and these particles do not exist naturally on Earth. We have to forge them. At CERN, this process starts in our complex of particle accelerators. We take ordinary protons, the hearts of hydrogen atoms, and accelerate them using powerful electric fields. They race around a large ring, gathering speed until they are traveling at nearly the speed of light. Their energy becomes immense. This is the first crucial step, creating a beam of highly energetic projectiles. Once the protons have reached their target energy, we slam them into a block of metal, typically iridium. The collision is fantastically violent. The enormous energy of the protons, as described by Einstein's famous equation E equals mc squared, is converted into a shower of new particles. For a brief moment, a zoo of exotic matter flashes into existence. Most are useless for our purpose, but among them, for every million collisions, a single precious pair, a proton and antiproton. Our job is to filter out these rare antiprotons from the debris. They emerge wild, with huge energy moving in all directions. To study them, we need to tame them. This is the job of the antiproton decelerator, the AD. As its name suggests, it does the exact opposite of an accelerator. Using a series of powerful magnets and electric fields, the AD catches the fast-moving antiprotons and forces them to slow down dramatically. It reduces their energy by a factor of about 100 million, taking them from near the speed of light to a more manageable pace. Even after their trip through the antiproton decelerator, the antiprotons are still far too hot, meaning they are moving too quickly to form delicate anti-atoms. The final stage of cooling happens in smaller, more refined devices called penning traps. Here, the antiprotons are held in a combination of a strong magnetic field and a weaker electric field. We can then cool them further by mixing them with a cloud of ultra-cold electrons. The hotter antiprotons bump into the cold electrons, giving away some of their energy in each collision. Slowly, the entire cloud of antiprotons cools down, becoming a placid, slow-moving swarm, ready for the next stage of our process. While one team is busy preparing the antiprotons, another team works on the second essential ingredient, positrons. Positrons are the antimatter equivalent of electrons. They have the same mass as an electron but carry a positive electric charge instead of a negative one. Fortunately, gathering positrons is a bit more straightforward than creating antiprotons. We don't need a giant accelerator. Instead, we can rely on a natural process called radioactive decay. we use a specially prepared radioactive source, most commonly a small piece of sodium-22. This material is unstable and slowly decays over time. As the sodium-22 atoms decay, they emit positrons. This provides a steady, reliable supply. However, these positrons are born with too much energy. They fly out at high speeds and in random directions. If mixed with antiprotons now, they'd simply zip past each other or annihilate on contact without forming a stable anti-atom. So our next task is to collect, cool, and control. We guide the positrons into a positron accumulator, a buffer gas trap. It's a system of electrodes and magnets. Inside the trap, we introduce a small amount of low-density gas, like nitrogen. The positrons collide with the gas molecules. Each collision robs a bit of energy, slowing them down. Eventually, they become slow enough to be held by the trap's electric and magnetic fields. Over time, we accumulate a huge number, hundreds of millions. They form a dense, cold cloud of antimatter in a tiny volume. This cloud is then carefully transferred to another penning trap. There they are stored and cooled until they're barely moving. We now have two prepared ingredients, a cold, dense cloud of antiprotons and an even colder, denser cloud of positrons. The stage is set for the most delicate part, bringing them together. Now we have our two populations of charged antiparticles, the antiprotons and the positrons, held in separate traps, cold and ready. The next step is the most critical and perhaps the most elegant. We must gently combine them in a way that encourages them to form a neutral antihydrogen atom. This isn't as simple as just dumping them into the same container. If the particles meet with too much energy, they will fly right past each other, or they will annihilate in a flash of energy. The key is to orchestrate their meeting with extreme care and control. This delicate mixing process takes place inside a sophisticated penning trap, sometimes called a nested penning trap. This device is engineered to hold both negatively charged antiprotons and positively charged positrons. It uses a carefully shaped electric field. You can think of it like a valley within a valley. The outer walls of the trap confine the positive positrons. A smaller potential well in the center holds the negative antiprotons. By carefully adjusting the voltages on the trap's electrodes, we can gently merge the two clouds of particles. We begin by pushing the cloud of antiprotons into the center of the much larger, colder cloud of positrons. The antiprotons are now swimming through a sea of positrons. Because both sets of particles are extremely cold, they are moving very slowly relative to one another. An antiproton drifts lazily through the positron cloud. Occasionally, one will drift close enough to a positron to feel its electric attraction. If the conditions are just right, if they are moving slowly enough, the positron won't have enough energy to escape the antiproton's pull. It will become captured, falling into orbit around the antiproton. At that exact moment, a new entity is born, a neutral antihydrogen atom. It is a remarkable achievement, the culmination of all the preceding steps. However, this creation also presents an immediate problem. The penning trap, which so brilliantly held the charged antiprotons and positrons, is completely ineffective at holding a neutral atom. The electric fields that kept the components in place have no grip on the newly formed antihydrogen. As soon as it is created, the anti-atom is free and begins to drift away, oblivious to the walls of its electric prison. Our next challenge is to catch it before it escapes. The newly formed antihydrogen atom is electrically neutral, so it slips right through the electric fields of the penning trap that created it. If we did nothing, it would simply drift until it hit the wall of the vacuum chamber, where it would instantly annihilate upon contact with normal matter. All our hard work would vanish in a tiny puff of gamma rays. To study antihydrogen, we must catch it. This requires a completely different kind of trap, one that can hold a neutral object. We use what is called a magnetic minimum trap, or an Ioffe-Pritchard trap. This trap works on a subtle but crucial property of the antihydrogen atom. Although it is neutral overall, the antiproton and the positron both have a property called spin, which makes the antiatom behave like a tiny magnet. It has a magnetic moment. This means it can be influenced by a magnetic field. The magnetic trap is an ingenious arrangement of powerful superconducting magnets that create a special magnetic field shape. Marketing. A cross-section diagram of a magnetic minimum trap, showing coils and field lines. The field is weakest at the very center of the trap, and gets stronger in every direction as you move away from the center. An antihydrogen atom in the correct state will be repelled by strong magnetic fields and attracted to weak ones. So, if an anti-atom is created inside this magnetic well, it will be gently pushed back towards the center whenever it tries to drift away. It's like trying to roll a marble up the inside of a bowl. Gravity always pulls it back to the bottom,